Hello everyone, and thank you for joining, and welcome to our final Contino live session of the year. Today's talk will be about mainframe and serverless integration, how to liberate the data and stay competitive. Now, just some quick housekeeping notes before we start. Today's session will be roughly 50 minutes long and will include a 5 to 10 minutes Q&A at the end. So if you have any questions, make sure to submit them during the talk, and I'll aim to answer as many as possible. Also, this session is being recorded, and everyone in attendance today will receive an email with a link to the recording. Okay, perfect. So I think we can start our session now. Mainframe and serverless integration. Before we jump into it, like a brief introduction about myself. So my name is Federico. I'm Contino's VP of Engineering for EMEA. I'm responsible for Contino's engineering resources, our technical strategy, our direction of travel of the company, and also our offering through the practices. I've been with Contino for the past 3 years and helping large regulated enterprises moving to cloud, building cloud architectures, building also cloud operating model, how to structure your company to get the benefits of cloud. I'm sure you all know Contino, all of you here. So let's just jump into the topic. So the big idea right now is that large payment providers are at crossroads. So from the 90s, the payment industry has been focused ruthlessly on reliability and resilience. All these payment providers over the years have been building their systems to achieve the highest level of reliability possible, high levels of 999s. Modern tech startups instead are coming at the same solution to a completely different angle. They're saying, no, we want to leverage the data that we have. We want to make sure that all the teams in our company can get maximum value of the data in order for them to provide innovative features for our customers. So the challenge is the following for payment providers. They have been sitting on this goldmine of data that is, however, kept in the mainframe. They cannot leverage the data in the same way in which startups can, which is a problem. So all these insights, all this capability that payment providers have and been unable to use them. So they understood that they need to evolve. Payment providers need to change the way in which they're thinking about their data and their business, moving from a place where they deliver resilient, reliable transactions to a place in which they provide real-time integrated services. They want to level the playing field with startups, incumbents. It's super important. So how to do that? Well, I'm sure you heard in the industry, there's a variety of ways to get data and make use of data in the mainframe. At Contino, we believe that there's a low risk and high value way to do it. So the way is to stream the data from the mainframe and making use of the data in cloud. What you do is that you replicate the information from the mainframe, stream it from the mainframe through your cloud environment, and in the cloud, leveraging cloud-native solutions like Managed Kafka or something like Kinesis on AWS, starting to process the data in the cloud, enabling 2 use cases. One use case, which is live transaction processing, defining triggers. Every time a transaction gets processed, a user receives a notification. But also enabling data analytics in this data, now in cloud, because now your teams can get a copy of data in the cloud and use a tool they want to extract value out of the data, to model data in the right way, to be able to do the same type of machine learning inference that small startups can do. But now, large banks can do it on their big data sets. So the theme here is that connecting the mainframe to cloud enables exploitation and storing of the data in an advanced way. Overall, this enables, yes, the company to generate insights and generate business value on the data that the company already has available, but also is a way to democratize access to data. So you remove the role of a gatekeeper of your DBA that controls the access to the database, and you enable a whole range of business units within the company to self-serve access to the data in cloud. Super important, and really a way for companies to level the playing field with small startups. So let's just take a look at this. So this will be a technical talk. we will cover some of technology's most important angles, if you want, of this. So let's take a look at the architecture, first of all. On one hand, as I said, we're streaming mainframe data onto cloud, leverage data in the cloud immediately for real-time transaction processing, to send notifications to our users, to evaluate whether a transaction is fraudulent or not. And then separately, we store data for long term, and then we enable all teams of business analysts, data scientists in the company to generate insights, to drive the company towards making data-driven informed decisions. It's a key enabler of functionality in a large bank. So the architecture, if you want, we're going to use AWS as an example here. The architecture extremely simplified. You can see it here. On one hand, on the left, we have the mainframe. Data from the mainframe is streamed via Kinesis onto AWS. We're using something like Kinesis producer libraries. So we have Java applications that receive data from the mainframe, typically via TIBCO or via MQ systems, send through this library to Kinesis, and then from Kinesis we have a Lambda function, a serverless function in AWS, processing the message, doing all the conversion that may be necessary if the format of the mainframe doesn't really match, maybe modern format. We're gonna have copybooks. All of this can be taken care of by the Lambda function, and storing data in DynamoDB. DynamoDB is the best, is one of the AWS NoSQL serverless offerings, database offerings, and is the best solution for low latency transaction. In this case, we're solving the OLTP problem. User or even another system in the backend of the bank can then go to AWS API gateway and consume data via another Lambda function from the database. So you see here that we have online transaction processing in AWS in our example with serverless only solutions. This is an extremely simplified view. You can easily, however, perceive a few things here. You can see, okay, I have now data that moves from a general purpose database that is serving a variety of use cases, both OLTP and OLAP in the mainframe, to a place where we're using a specific database to solve a specific business problem, and where our database allows for performances that would just be impossible on the mainframe. This is why we're using Dynamo, because Dynamo can respond in sub 10 milliseconds responses back to Lambda. So you can see as well that in a case in which we have online transaction processing of payment transactions, well, this is a very latency sensitive system, and our design allows us to be as careful with time sensitivity as well. So I know that most of you will be familiar with AWS, but I want to give a brief introduction about some of the core AWS services that we're going to cover through this presentation. So on one hand, we have the standard AWS serverless services, AWS Lambda, function as a service. But then we go down the stack a bit, and we also have Fargate to run our containers. Where Lambda doesn't get us, where Lambda has limitations, Fargate steps in, and Fargate allows us to use containers and perhaps to run and execute a function or a process for longer than the limits that Lambda has. Then we have, as I said, a suite of Kinesis services that manage really the transaction processing, message processing. And then we have a set of different databases. Dynamo, as we said, NoSQL, key value. RDS, which is a SQL server, typically a SQL database. Postgres, Microsoft SQL Server, whatever you want to use in that case. And then Amazon Elasticsearch. Now, as you see, data gets replicated in different ways, in different databases, because now these databases enable different use cases. This is how we use microservices in this case. So if we jump into the architecture right now, and you can see that the architecture now is not as simple, there's more complexity from the original one. We start seeing that in a real use case application, as the one that we've been doing as well for some of our clients, well, complexity is significant. Complexity is significant in the sense that we have multiple Lambda functions building doing different activities and building different components of the system. We have focus on performance for the OLTP, and we have a clear critical path, such as our transaction can be processed in the shortest time possible. And then we have long-term, well, relevant storage in DynamoDB for long-term as well, where appropriate. And then we have, on the third hand, user getting access through their data from API gateway. This user can be an external user of the bank that reaches, calls an API endpoint and fetches their transaction for the past 24 hours. Or it can be an internal system of the bank that fetches all the transactions of all the users in the past 24 hours. You can see as well in the bottom part of our diagram, we have the data lake for long-term storage of all-up system, or all-up data. So the transactions, making them available for our analysts. The analysts are not going to Dynamo, but they're going to the data lake, data stored in S3 as well. We'll see in a moment how it works. At a glance, just to give you an idea of the complexity of the system as a whole, this is by no means a simple system. We have a mixture of a serverless and microservice architecture dominated by Lambda, but spread across multiple microservices with tens of functions as well, serverless functions, shared kernel, lightly versioned, so microservices that share their ability, the connection ability, with significant latency requirements. The core pattern is an event sourcing pattern that lends data to a data lake for consumption by the analyst. We can see that in our case as well, it was very important to define the microservices boundaries. So we see that because we have so many microservices, so many Lambda functions, I don't want to spend too much time in this talk talking about domain-driven design, which was the strategy we've used and we recommend to use to define the aggregates, define the boundaries of the microservice. Instead, I want to say, remember that in a large organization, when you define the boundaries of your microservices, think about the operational needs. Think about who is going to operate this, because you will see that in our design, some of the architectural choices to define the boundaries between the microservices are not only based upon what makes sense from a domain perspective, but also they are based upon who is going to run this system after us. Let's just now spend a minute to look at the architectural highlights, some of the architectural highlights. The biggest challenge, obviously, for this type of systems in which you're replicating data in multiple databases is to ensure the consistency or correctness of the data. So whether because everything was in one database before, and everybody, both internal systems as well as external users, were getting access to the same data set, we had a golden source by definition, and there was no need to ensure correctness of that per se. But in our case, because we're moving to a distributed system, and because we're dealing with transaction data, well, we need to make sure that the data is correct, really correct. We need to define even what correct means in our case. So we define, in other words, non-functional requirements, which is the first step of thinking about ensuring correctness across multiple databases. We see in our example, we're not going to dwell in it, but we see in our example that there are different levels of correctness, consistency, and latency that we define. We define SLOs, service level objectives in this case, that are really precise. We say 99.9 of GET API calls for the transactions over a minute will return correct data that is not older than 30 seconds. So the step one of our process of defining how to address the correctness problem is to define what our goals are. So what is expected level of consistency, the expected latency as well, because we not only want to get all the right transaction data, we also want to get the right transaction data within reasonable timeframes. So in order to address this, a lot of work has been put into it. We start with an end-to-end testing system that adopts a end user perspective and verifies the formal correctness of the system. We see that in our case, you can see in the diagram, that we have multiple probes that have multiple vantage points. Some probes have, are embedded in the cloud. Other probes are outside. They allow us for a system of continuous testing and injection of synthetic transactions, both in the development staging phases of the project, but also in production, making sure that all our functional and non-functional requirements are clearly respected. Because transactions have a complex logic, some of the system was built. So we decided, based upon some libraries, to build these components and say, okay, we're building some of our logic because we think that our logic is too different from what we find outside in the industry. Other parts of the system, instead, they were just targeted at performance testing, latency testing. Those ones, instead, we just bought, if you want. We use standard tooling available in the open source world. We can see as well that the end-to-end testing system triggers notifications. Some of these notifications are solved by humans, if you want. Some of these notifications are not solved by humans and are instead taking a longer time to execute. And they are sent as notifications to automated systems that try to resolve them. We can see in the end that we've also built two separate transaction reconciliation systems. These two systems ensure the correctness of the data between the mainframe and the databases that we have. On one hand, we have an in-band transaction reconciliation system based on the at least once guarantees that all our systems have. So we use idempotency keys, idempotency tags or idempotency keys, and a number of retries in places to ensure that transactions get to the end place where they should get. We have monitoring, alerting, and a system with a high watermark that tells us this is where the database got to. This is where the mainframe is. Yes, you have a gap, and maybe the gap is acceptable within the constraints that you set, or no, maybe the gap is just too big and is not acceptable within those constraints. But this is based upon the usual kinesis streaming system. Then separately, out of band, not uncommonly in banking, we have a different system, complex system based on Fargate and AWS Lambda with step functions, AWS step functions, Fargate and step functions, that uses a different data source, a batch data source, and processes transactions in a different way. Now, rather, the mainframe says, every hour, here is a list of the transactions that I've sent you in the past hour. And then the Fargate container checks and says, yes, I have it. No, I don't have it. Let me see what I can do to fix it. Once again, high watermark in place, monitoring, alerting enabled. But we've seen here that because of the transaction reconciliation system complexity that we start seeing here in this diagram now, well, we reached some of the limits of Lambda, especially the execution time. Our system can take more than 15 minutes because we may be in a position where we have to reconcile data that is days old. And so we want to use a container that allows us to process for a potentially limited period of time. A different architectural highlight that we can focus upon is the full text and advanced search. So I'm sure you know, a lot of you will be searching your transactions. If you think about this, a lot of you will be searching your transactions in your mobile app. So you open your mobile app and you say, oh, I want to search in my bank statement, what is the transactions that I made in that merchant? And I started doing full text search. I had a few letters of the merchant name. The problem with that is that this is really hard to codify in SQL. You can do it in SQL, but comes the performance impact. Instead, in DynamoDB, NoSQL world, you just cannot do it. It's just not feasible. You need a complete table scan to get to which type of rows contain which merchant. So there's a lot of complexity. Dynamo is just not correct for the use case. So we're using the standard search database most commonly used, which is Elasticsearch. This enables users to search for their transactions rather than going to Dynamo. They still reach the API gateway. They still get to a Lambda function, but the Lambda function knows that it needs to get to Elasticsearch. We're using a standard feature of Dynamo called DynamoDB Streams to replicate data in Elasticsearch, and we're using ultra-warm as well for low-frequency data that is not accessed that often. If you're doing full text search on your transactions that took place in 2005, probably you don't need to have the response in under 10 milliseconds. In all of this, there's a number of systems as well, including RDS proxy and caches to avoid, if you want thundering herd issues, to avoid that we are impacting some of the downstream systems, throwing too much requests to those systems, especially because if you can see in the diagram, in the center of the diagram, we start having also, top right diagram, we start having also a database, SQL database. So why do we have a SQL database in there? Well, in our full text search, we had a need of include advanced search, a need to include some reference data. Static reference data set, perfect for a SQL use case, ends up in RDS and gets joined in memory with a Lambda function. Now, I'm not a huge fan of joining stuff in memory because I'm aware of the performance implications of that. But for our use case, because the size of the reference data set was as small as we thought it was, we decided it was okay to do it because we gained some advantages out of that. So we can see here as well that once again, it's a simplified diagram, but it's a very relevant one. Some highlights here, once again, you can see that the number 3, the Lambda function at the bottom, connects not only to Elasticsearch, but also to RDS, and then returns responses back to the API. So another architectural highlight that we can talk about is the data lake. So as I said, we're not only extracting data from the mainframe to enable our OLTP use cases, we're also extracting data from the mainframe to integrate data with our data lake. Data lake is really where the value is. So we want to liberate the data for wider consumption. Our data analysts, our data scientist teams, don't go to RDS. They don't go to DynamoDB. They go to S3. Why do they go? Why do they go to S3? Well, because by going to S3, we can enable them, and using the Hive meta catalog, using standard catalog system, data catalog system, we can enable our users to then query the data in the fashion they want. So users can use Power BI if they want to use Power BI. They can use QuickSight if they want to use QuickSight. They can use Redshift or EMR and pull data out, even Redshift through Spectrum by reading data directly in the buckets. So we give the users an ability to query the data in the fashion they want. We can also willingly charge the users for the data they query, so charge the systems within the company for the utilization of the data. We can do a lot of different things. The data lake is not the focus of this topic, but there's some complexity here. So we're doing different steps, data cleansing, we enrich the data as well. The number of jobs that would happen here as well. The key takeaway is we enable the systems where data is now being democratized. We standardize the access to the data by leveraging the Hive meta catalog, which is the standard way to open up access to data. In the end, what I think is the last architectural highlight is the event source. Clearly, we have a microservices system. We want to enable a lot of our teams to do a lot of work with the transactions that arrive. We want to enable our fraud team to check that each one of the transactions, to check whether a transaction, incoming transaction, is fraudulent or not. How do we do it? Very simple. We create this event source and we tell our fraud team, listen to the event source, and anytime you find something that is off, let us know, or deal with it depending on the logic. So this enables strong decoupling once again from our system to the others and moves the layer of integration between the different systems from an API into the format of the transaction payload in the event source. This is where the API now is between different microservices, is the format of the message. This is why we use Pact. We would recommend using Pact for contract testing. This is not a full event source in the sense that we cannot replay history because we're using Kinesis for this, but nonetheless, it satisfies the needs of OLTP processing, enables us, for example, to notify our users on their mobile application or on their phone just by sending an SMS or a phone call every time a transaction takes place. Now, some focus in the next 5 minutes for our call about our serverless patterns. So what do we need to look after when we're building a serverless systems at scale like this one? First point that we make is that we use a circuit breaker pattern. Super common. When you build a microservices system, you have requirements for consistency and availability. When you don't want to, when you want to have a fallback system, when you don't want to flood a downstream system that is already down with further requests, what do you do? And reduce henceforth the resource consumption of the downstream system. Well, you break the circuit. In our case, what did we do is the fact that we knew that we had mainframe already available and the data in AWS. So we can, by having this circuit breaker at a middleware layer between all the calls, we can say, okay, if the cloud is not available, we can fall back on the mainframe and go back, ask the same data set to the mainframe and obtain the same results. It's a very good way also to ensure a smooth transition between one system and the other. It's very commonly used system very commonly used pattern in distributed systems. Then one thing to think about building systems with Lambda absolutely is the control function scaling and throttling. On one hand, you don't want to have too many Lambda functions running at the same time that can exhaust both your account quota, but also can affect your downstream systems. So you want to control how many Lambda functions are running at the same time. And you want to also make sure that you're considering monitoring around that. For this, you want to, when you're thinking about monitoring, thinking about tail latency events, not looking at the average, but looking at the 90th percentile, looking at the 99th percentile, depending on what is your performance appetite. And in the end, we recommend using provision concurrency to make sure that you reduce the cold start problems on Lambda. Provision concurrency ensures that at all times you have a warmed up Lambda function. Other cloud providers like GCP will have a very similar solution to provide the same level of performance on their GCP functions. So talking about serverless, one of the common problems is the impact on downstream systems. Very simple use case. I have 1 million concurrent users. They can all connect at the API gateway at the same time. The API gateway opens up 1 million Lambda functions, 1 million connections to 1 million Lambda functions. 1 million Lambda functions want to read data. If they go to Dynamo, that's not a problem. Dynamo can definitely handle 1 million concurrent transactions. It's just the way in which it was built. But you cannot go to RDS in the same way. You cannot go and open 1 million connections to a Postgres database in the same way. So you need to control the scaling. You can control it in multiple ways. In some cases, you can use a message pattern and controlling number of messages in the queue and messages that are processed from the queue in a way that you're checking RDS for no more than X concurrent Lambda functions and henceforth X concurrent connections. That doesn't work all the times, depending on your use case. In our 1 million connections example, it would not work clearly because you cannot respond immediately, but it would work in a webhook system. On the other hand, the most commonly used pattern is RDS proxy. So we're creating a proxy system that helps us, let me just turn the lights on, sorry. We're creating a proxy system with RDS proxy that helps us keeping the connection pool alive. We're using connection pooler. Nothing new here under the sun. Connection poolers have been in place for years. Postgres, SPG bounce, PG pool. In our case, with RDS proxy, we're using a cloud native solution to achieve the same goal, which is keeping a number of connections alive towards database and opening a higher number of connections to the pooler that then are processed one after the other. In the end, last topic for the architectural highlights of the system is looking at dead letter queue patterns of Lambda. Now, there's a bit of complexity in this because so far we have been thinking about this integration between Kinesis and Lambda in a way in which we said, oh, but you know, it's very easy. We can just process one message after the other. We typically don't do that. We have micro batches. Processing micro batches is way more efficient than processing a single message. If you're processing a batch, you're faster than processing one message after the other. This generates problems though. When dealing with messages that fail, there's a poison pill. There's one message out of 100 that causes a failure in the Lambda function because the Lambda function crashes. Our entire batch will need to be replayed or disregarded. So what do? We control with some of the AWS proprietary logic how to handle this use case. We use bisect on failure in a use case. So you help by using bisect on failure, you can have a performance impact on the overall system, but also you can be more precise in identifying exactly which message should be executed. Should be sent for further analysis. Consider that in our systems, we have at least once guarantees in a number of places. So replaying the same message 20 times in a corner use case is not really a problem. We have checks in place that ensure that we don't book the same transaction twice. Now, let's just look at a moment at developer experience. So how does it look like building on AWS? So CI/CD, in our case, there's a number of ways to do this. The key takeaway is the fact that in our case, we've been using the AWS developer tools to build all of this. We've been using monorepos for the functions and a continuous deployment with multi-branch pipeline. The serverless framework as well has been essential and a core tool for our Lambda functions. We use Terraform for most of the infrastructure resources, but we've used the serverless framework for the Lambda integration with the Lambda function. Unit and infrastructure testing in the pipeline, and canaries being deployed multiple times. Canaries allow us to test a deployment with a small percentage of traffic. One of the common challenges for serverless is also how to do local debugging and local deployment. In our case, we're using local stack. Integrated with IntelliJ using the AWS toolkit to test and debug Lambdas, we can make ample use of AWS. We made ample use of AWS X-Ray and AWS CloudWatch as well. But in our case, local stack enables a user or developer to test the entire stack on their laptop and be way faster at testing integration between piece of code and Dynamo than having to deploy on AWS at all times. Local stack has been a significant change for our developer experience, developer work. Let's just now spend a few minutes looking at performances. So obviously, we're dealing with a distributed system that generates millions and millions of events at all times. So we need to go really deep in the level of monitoring that we're doing. We're doing performance monitoring, leveraging all the tooling that we have available, Lambda Insights, function summaries is really important. Because if you have an event that happens every 10 million transactions, well, it can happen all the times. Every minute we generate 10 million logs. So we at all times. So looking at performances means looking at trends, and especially looking after tail events that happen in a subset of cases, but can impact a large percentage of your users when you're operating at scale. We've also had a significant challenge in our case, which is measuring for real. So as most of you will know, in the transaction processing world, in those worlds, we need to make sure that transactions are processed in a reasonable time frame. So, and distributed systems are hard to tackle in this, hard to tackle because you need to ensure that the clocks are synchronized. Here is where we find the limitation of Lambda, because we cannot configure the NTP server where Lambda is running. So we did some tests around this to understand exactly what would have been the implication of this. Our tests are not clearly not final, but we can see that where there is a 40 milliseconds distance between the data center and AWS, the offset is around 10 milliseconds. It's a significant offset that the clocks have. If you have to measure when an event happened in multiple places and you have to henceforth synchronize the clocks to ensure that you know exactly when something happened, you may have a challenge with Lambda, and you need to take into account that the challenge may not be controllable, but maybe it's just not relevant for your scale. if you're operating within 2 to 5 seconds for each API call, you don't need to worry about a 10 seconds offset, 10 milliseconds offset. Response time is really important as well. We can see here that the response time, and we have a slide on this in a moment, there's significant variability between the average, the tail, and the max. Not uncommon in distributed systems to have this variability, or if you want, this number of standard deviations in this. But at the same time, it's something to take into account, and where something like AWS X-Ray helps you understanding where is the gap. Distributed tracing in a world of microservices is a necessity, it's not a luxury. So performance samples, as I was telling you, in our case, some numbers here, less relevant as hard numbers, more relevant as some indications. In our work that was based on Java with some limitations as well around Java itself, we can see that the time that a transaction takes from moving from the mainframe to being available on the API gateway, so mainframe, Kinesis, Dynamo API gateway, can be the average at only 30 milliseconds, the max at 2 seconds. So this is a significant impact. There's orders of magnitude between one and the other, especially because the P95 is at 37.2 milliseconds. You can see that we go really far in some cases. Once again, it can happen in distributed systems. It may be fine in your use case. Some recommendations really quickly about this, some takeaway, systems optimization. So in our world, Java can be optimized for latency, low latency on Lambda. So Java is not a no-go by itself, by any means. And also take into account the AWS, the features that AWS offers on their services to optimize performances. Enhanced fan-out on Kinesis not only increases throughput, but also as a result, reduces latency. Lambda destinations is important to control to control the messages that fail, the processing. And also provision concurrency, really helpful to reduce the cold start problem. I will say though that when we're looking at performances, we were very concerned about a cold start impact of using Java. We said, oh, Java will take a while because the JVM needs to be spun up and it will take a while. Curiously, and perhaps counterintuitively, in our samples, in our measurements, fine-tuning the Kinesis batch size, the micro batch size that each Lambda function needs to process, has more an impact on the average latency end-to-end of the system than JVM-specific optimizations. Very interesting, right? So we're looking at the infrastructure as a bigger impact than Java, which can be somehow counterintuitive. In the end, let's spend a few minutes looking after the cloud operating model, thinking about how we can build a system that is based on serverless in a company that perhaps is not as cloud native as most banks are, most financial institutions are. So first of all, one thing we have to realize is the fact that by moving to a serverless system, on one hand, we're pushing a lot of responsibilities onto our cloud providers, because against on-premises, a lot of the networking, storage, serverless servers, virtualization concerns are left onto the cloud provider. We don't worry about that. We only worry about our code, the logic of our application, plus some performance tuning, as we've seen before. So fully serverless means that we're pushing responsibility onto the CSP to increase our ease of support, to reduce our maintenance costs, to enable our developers to be faster at deploying, faster at creating features, increasing the velocity of the teams. This is why we're using serverless. The problem with that, however, is the fact that some enterprises, especially right now, they want to leapfrog digital transformation. So they want to move from a place in which they have been historically building with VMs and optimize policies and processes for applications deployed on VMs to a place in which they are using serverless functions that result in higher risk, more complexity, and the usual problem, which is what I call no man's land of compliance. In other words, you have a team that is using technology so advanced that your internal processes have not been ready to support, have not been scaled up to support. For example, we've seen this, perhaps unsurprisingly, a number of times in which you have compliance function that says every deployment of code in our company needs to be on a VM that runs on an antivirus. But you don't really run an antivirus on Lambda. There's not a technical way to do it. And it may be hard to having to explain that to your compliance or security teams. It's way easier if you bring them on the journey with you at the beginning and you go with them to build that. So rather than jumping directly into serverless and just building things. In particular, your company as well that is just gone to serverless can also have low levels of engineering maturity, can have low levels of maturity in the way in which they're adopting technology. So the company is not ready to make use of serverless per se, which can result in challenges when adopting technology at scale by multiple development teams. We're thinking of switches as well. When you're building a system, either a new greenfield or a brownfield, trying to evolve the system, trying to migrate the system, or re-architect the system, what can you choose in a system in general? You can choose the architecture of the system. I can choose whether my system will be run on a VM, will be run on a container, will run on a function, or I can choose the reusability. How many of the building blocks that I'm going to create will be specific for my project or will be used by other projects in the company? Should I make my system really generic that anybody else can use it, or should I not? I can look at the talent as well, and talent is a proxy for engineering maturity again, so I can try to give more time to my people to upskill, or I can bring external resources that can help upskilling my people. Either way, I only have a subset, a number of controls that I can play, which leads me to think and try to connect this into a coherent story, which is a big takeaway. And there's another talk that you can watch on our Contino webinars exactly about this that goes more in depth to what I'm doing today. But the takeaway of the session of this cloud operating model idea is that at low levels of engineering maturity, in other words, when your teams are not ready with serverless because they haven't been built serverless, because the company has not structured itself to leverage serverless, we can break the link between cloud architecture and operating model. In other words, if your company has never used serverless and you're building a serverless system, it may be a challenge for you to operate a serverless system with an operations and a development team. You probably want to have autonomous teams operating your functions. But in order for you to have autonomous teams operating your function, you have to create cloud operating model. You need to create an IT system, IT structure, IT department in the company that has those autonomous teams. If you don't do that, if you try to use serverless without taking security and compliance and the organization itself with you, you will find struggle. This is how we hear a lot of times from our clients, this or that technology doesn't work for us. In reality, companies, in my experience, are very eager to do tools-based transformation, just changing the tool, but not changing their structure to support the tool. So before we close, I want to leave you with a couple of key questions when thinking about whether you should migrate your mainframe to AWS or to your cloud providers using serverless, using different technology. The two key questions you want to ask yourself before embarking on this journey is to say, what is our level of engineering maturity? What operating model are we going to use? Who's going to support this? In a way that your enterprise architect, your system designers, your solutions architect can help define the right system based upon not only what is the right technology, but also what is the structure in the company around this. And don't be afraid, in my experience, of making compromises that allow you to get a win rather than being over ambitious and targeting technology for technology's per se. So thank you very much for listening to my talk. Now, if there's any question, it's a good time to ask the question. Let me just see if we have any question. So we have a couple of questions. So there's a very, very short question, which is how long was the project? So how long does a project like this take? It really depends on a number of things, I'm sure, but orders of magnitude in the months. So you will take some months for sure to build this complex architecture. And there are two stages. There's a build phase, really the initial build phase, and then there's a run phase. And all the optimizations around this, because the bank needs to be very careful with the way in which data is deployed across multiple databases to ensure the correctness and ensure a level of comfort within the bank that there's the right direction of travel. So we're talking about months. And in the end, second question, can you explain again why there are so many databases? So as you remember, in our architecture, we have multiple databases because rather than having a single database on the mainframe, your DB2 system will do OLTP, OLAP, will do transaction processing, will do analytics as well, do a number of things. But in our case, we're moving to cloud, we're creating microservices. So on one hand, we want to give autonomy to the team to choose the best tool to solve their problem in a way that the teams are not constrained by the choices that others have made, but can operate at their speed. So number one reason you have different databases. Number two reasons is also performance. Performance is really important because we live in a world in which by using Dynamo, we can respond orders of magnitude faster than the mainframe can do on premises. You'll see that in a lot of cases, when you open, the example is when you open your mobile application of your bank, whatever is your bank, you're not gonna get a list of all the transactions that ever took place on your system, in your statement you ever done. You will see a subset of the transaction. This is because the API goes back and requests for a subset because you cannot respond with a batch that is too size. You paginate, it's a pagination system, right? It's a pagination. But with Dynamo, you can respond with way more transactions, be really, really faster because of the nature of the database. So by using a specialized database, we can be way, way more performant. And the third reason, in the end, is quite frankly, is the fact that the direction of the industry relies on the separation between storage and compute. With storage getting cheaper and cheaper and the cost per gigabyte getting so small, it means that we don't need to worry about the fact that we're storing the same data set across multiple databases. It's not a concern for us. We gain way more in terms of velocity than what we lose in terms of cost. So it's a trade-off worth making. Why so many databases? Three reasons. Give autonomy to the teams, performance to ensure the right and maximum level of performance is achieved, and also because it's not too expensive to operate. Perfect. I'm going to give a few more seconds if there are any other questions. Okay. I don't see any other question coming up. So yes, if there are no more questions, I think we can end here. Thank you so much for joining. I hope you found today's session interesting. Make sure to check out our Contino Live webinars on contino.io/events on our YouTube channel. Goodbye, everyone, and Merry Christmas.